We'll make this quick since it's Friday. Well, hopefully I'll make it quick. Sometimes I say that and then I don't really mean it. But this one, it's basically just the exact opposite of what we just did, which is weak acids. So now we're talking about weak bases. And there's only a couple of things that are tricky here. With a base, you're just looking for the exact opposite. It's the thing that accepts a hydrogen from something else, right? So the water here is acting like the acid. It gives a hydrogen to the NH3. It becomes NH4+. So NH3 is a base. All right? Over here on this side, the conjugate base, OH minus, accepts a hydrogen from the NH4+, turns into H2O, so it's also a base. All right? The equilibrium constant expression, we use Kb instead of Ka. See, because it's a base, so, it's a B instead of an A. But it's the same thing. It's just an equilibrium constant, all right? And in the expression, instead of HA, we use HB, okay? So your basic, your general base reaction here would be B minus plus H2O gives you HB plus OH minus. Okay. Now the bad news on these, maybe some of you don't care, there's no shortcut way to write a base reaction like there is with an acid reaction. All right. You have to have the water in there because the water is what's giving the hydrogen to the base to form the OH minus. All right. So in this case, in the base reactions, the water has to be there. But it's not an equilibrium expression because it's a pure liquid. So that's how you would write your equilibrium expressions for that and your equilibrium reactions. So again, I mean, just basically the exact opposite of acids. Now this is the part that's going to give you a little bit of trouble recognizing something as a base in the first place. Because with an acid, it's really easy. All it is with an acid is it's something that gives away a hydrogen. Well, there's going to be a hydrogen on the front of the molecule, right? So you see HCl. Oh, there's an H. That's an acid, right? With a base, it's not quite that simple. NH3, ammonia, it's got hydrogens on it. So you might think, oh, well, there's an acid because it has some hydrogens. Well, actually, ammonia is more of a base. So I think the book talks about, it's not in these notes, but the book talks about there's two things you're really looking for, and this will be good enough for this class at least. One type of weak base. Well, okay, now let me say this. Strong bases are easy to identify, right? Because what do strong bases all have? OH, right? A hydroxide. So you could have NaOH or KOH, whatever. That OH is a clear identifier. This is a base. But with weak bases, they don't have that OH attached on them. All right? So that's, well, I mean, this one does, hydroxylamine. But it's not actually the OH that comes off here. It's going to accept the hydrogen from somewhere. So what you're looking for with these is one of two things. Number one, you're looking for nitrogen. Okay, now it doesn't have to be nitrogen, but what you're really looking for is a lone pair of electrons somewhere. Why a lone pair of electrons? Yeah, because you've got an H+, you basically got a proton floating around. It doesn't have any electrons to share with anything else, so it needs an electron pair. All right? So thinking back to your Lewis acid-base definitions, this kind of makes sense, right? Okay, NH3 is a Lewis base because it's an electron pair donor, right? It's got this electron pair that it can give. The H+ is a Lewis acid because it's an electron pair acceptor. It's going to come in and bind with this. And so, you can kind of see where that Lewis acid-base definition came from in the first place. The reason you're looking for nitrogen is because nitrogen compounds, nitrogen, when it forms compounds, really tends to have a lone pair somewhere on it. Okay? It happens a lot with nitrogen. So it's not always nitrogen. For example, you've got the HS here. You've got CO3 2-. But the ones up here, if it's got a nitrogen, if it's got a lone pair where a hydrogen can come in, then it's probably going to act like a base. All right? So that's one way. Now, the other thing you can look for is kind of like these bottom ones here. They're all anions, right? If something is negatively charged, it's much more likely to gain a positive hydrogen than it is to lose something else and become even more negative, right? So if you've got an anion, a lot of times that will be a good base. Not always. And we've talked about some of the things that are anions that do not act as bases, like Cl-, right? Anything that's a conjugate base of a strong acid just doesn't really even act like a base at all, okay? But a lot of things that are anions will accept a hydrogen. So those are kind of the two things that you're looking for, and that'll tip you off, oh, this is a weak base that we're talking about here, all right? So that's kind of the one tricky thing about bases that you don't have with acids. pH of a 0.15 molar solution of NH3. So to solve for this one is basically exactly the same as solving for an acid. You're just using a base equilibrium instead. And then there's a couple of things you have to watch out for at the end that can kind of get you. One thing is what we're ultimately going to be finding in our ice table here is not an H plus concentration. We're going to be finding an OH minus concentration. So then you're going to find the POH by taking the negative log of that, and then you're going to have to flip that and change it to a pH because they're asking you for a pH. So just a couple additional steps you have to watch out for on the base problems, but they're really similar. So there's your Kb expression for that one. The Kb for this reaction, so we would say the Kb for NH3 is 1.8 times 10 to the negative fifth. Okay. I don't know why they set this up this way in the notes. They just got rid of the change step for some reason. I don't like that, so I'm going to change this to change. And then we'll put our equilibrium box down here. Otherwise it's an IE table, and that just doesn't have the same ring to it. I like ice better. So you've got your NH3, which is initially 0.15, and then you've got 0 and 0 on the NH4 plus and the OH minus. And again, the reason that those are the ones we care about is because those are the ones that are in the equilibrium expression. We don't need to worry about the water. Okay? These are still in a 1-to-1 ratio, so with bases, just like with acids, you've got nice 1-to-1 stoichiometry. Pretty much for this whole chapter, that's all you really need to be thinking about is 1-to-1 stoichiometry, which makes it nice. This is going to decrease by x. This will increase by x, increase by x. So now we've got x, x, and 0.15 minus x. Same issue with these. We don't want to deal with quadratic formulas, but the Kb for this one is relatively small. It's 1.8 times 10 to the negative fifth. You might check this at the end just to make sure. But I'm guessing that the amount that actually changes into these two things is very small compared to the 0.15 that we start with. So we're just going to say 0.15 minus x is basically 0.15. Okay? So then when you plug this thing into your equation, you're going to end up with, I got the Kb already, 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth is equal to x squared over 0.15. Solve for x. When you do that, and I think this is in the book, when you solve for x here, you should get 1.6 times 10 to the negative third. Okay? So then we might check that just to make sure. If you take the 1.6 times 10 to the negative third and you divide that by 0.15, and then multiply that by 100, it's 1.1% ionization. So we're fine. As long as it's under 5%, we can make that assumption that we made. So our OH minus concentration at equilibrium is 1.6 times 10 to the negative third. Right? So then you take the negative log of that, and that's going to give you, I just don't feel like doing all this on my calculator today. 2.80, but again, that's your POH, right? 2.80. So then you just subtract that from 14. That'll give you your pH, which is 11.20. Did I do that right? Yes. Mental math. All right. So that's that. I mean, it's really not. Oh, it's writing all this stuff in. Never mind. And I had all of this too. Oh well. I like it better when I write it. So then your pH is going to be 11.20. All right. So nothing really complicated there. It's basically the same process we've been using. Basically. Okay, so solution made by adding solid sodium hypochlorite to enough water to make 2 liters of solution. Has a pH of 10.5. It's giving us the Kb, and we want to calculate the number of moles of NaClO that were added. So that's a little different. Not much different, but a little different. Well, I guess that's a little bit different, because what we're doing is trying to find an initial instead of, trying to find a final concentration. They're giving us the pH to start with, so we're essentially just working backwards on this one. So what's maybe the first thing that we would want to do on this one? Okay, maybe we could turn the pH into a concentration. So 10.50. Now the question is a concentration of what? The base ion. Okay. Why don't we write an equation for this first? That might be a good idea, right? So we put in NaClO. Now with NaClO, as soon as we put that into water, what's it going to do? It's going to ionize, right? So it's going to split up into Na+, which I don't care about at the moment because it's not doing anything in the solution, ClO-, all right? So really our base reaction here, and again, these are a little tricky, just writing the reactions in the first place, figuring out what's going to happen. But we've got ClO- in water. It's going to become HClO plus OH-, okay? So what concentration might it be helpful to find as far as our equilibrium is concerned? Say it again. Yeah, I mean, our H plus concentration is not going to do us any good here because that's not in our equilibrium equation, right? But if we find the OH- concentration, then that's going to help us with our ice table. So again, I like working with the pH, POH better because you've just got easier numbers to work with. So let's find the POH first and then take the antilog of that. Very controversial term. So the POH would be what? .50. All right. So then basically we tend the opposite of that. So then you've got your OH, where did I write this? I'll write it over here. OH- concentration is going to equal 10 to the negative 3.50, right? Does that make sense? I'm not making too big of a leap there, am I? Okay, because I'm just trying to shortcut this thing as much as I can. So 10 to the negative 3.50 gives me 3.16 times 10 to the negative fourth. How am I sig figs? 3.2, I guess. Because there's only 2 sig figs in that pH. So 3.2 times 10 to the negative fourth. That's my OH concentration when? Initially? That's my equilibrium, right? Because I got that from my pH. So make our ice table. We know this probably started out as 0, right? And now we have 3.2 times 10 to the negative fourth. So this must have, so now we can fill out the change row here. This must have gone up by 3.2 times 10 to the negative fourth. Everything's 1 to 1. Plus 3.2 times 10 to the negative fourth. Minus 3.2 times 10 to the negative fourth. And we don't care. So then we're going to have to use x's for this next part. Okay? And we've got the KB. So this is going to be x plus. Well, but that doesn't matter. We got to plug that into the, well, we need to find the initial, but we're going to have to probably use our equilibrium first. Okay, so here's what we have to do. We've got the KB. Sorry, got stuck there for a second. We've got the KB. We know everything except for the CLO minus, right? So then just plug that into your equilibrium expression. You've got 3.3 times 10 to the negative seventh is equal to your two products, 3.2 times 10 to the negative fourth squared over, and then we'll call this x for now, okay? So then you just basically solve for x. That's going to give you your equilibrium concentration of your CLO minus, okay? And then we can use that to kind of work backwards in our ice table. So oh, I see. They're using x. They're just solving for x initially. I think this will work, though. Let's try it this way. Because this way makes more sense to me. 3.3 times 10 to the negative 7th. Whoops. That's not right. Divided by 3.3 times 10 to the negative 7th. So that should give me an x of 0.310. Or just 0.31. I guess we're working with two sig figs here. Okay? So then if I want to know my initial, I would just add those two together, right? So 0.31 plus the 3.2 times 10 to the negative fourth that we subtracted from it. And we'll see. It'll be interesting to see if this makes a difference at all. To our sig figs, it's still 0.31. Yep. So, and that works out the same way as the book. They do it a little bit differently. They call this x up here, so then they call this x minus 3.2 times 10 to the negative fourth, which I guess you could do it that way too, and then you plug it in down here. But then do they have to make the assumption? No, I guess they don't have to because that's your only x. My way is easier, as long as it makes sense. So then you end up with 0.31. That's your initial concentration of the CLO minus, right? Now what they're asking for is the number of moles of NaClO that got added. Okay, so we've got our molarity. So you've just got to think about your equation for molarity, moles over liters. So we've got a volume of 2. We've got a molarity of 0.31. Multiply those together. That will give you your number of moles. So 0.62. Now that's the moles of ClO minus, right? But this thing dissociates in a 1-to-1 ratio because there's just one of each. So that's also going to be 0.62 moles of the NaClO that was added. Okay? So that's kind of how that works. So it's a kind of a nice little problem because it works backwards from what we usually do. All right, Ka and Kb can be related to one another by the Kw. All right? So kind of a nice little thing. This is on your equation sheet as well, so you don't have to worry about memorizing this. But there's all these relationships that you can have between all these different variables that can be helpful in certain situations. Sometimes if you know the Ka, it's nice to know the Kb, all right? So now notice here, this is actually putting numbers on something that we said earlier in the unit. If you've got something like HF, which is, relatively strong acid, okay? I mean, it's weak, but it's got a fairly large Ka compared to others. Well, its conjugate base, F minus, is going to be really weak, right? Because it's a much smaller number there for the Kb, all right? So stronger acid, weaker conjugate base. And now you can see it with numbers. But remember, Kw is 1 times 10 to the negative 14th. Whoops, 14th. Now another relationship that you can have here, the pKa plus pKb, because we've already done this before, pKa plus pKb, if you take the negative log of everything here, is going to be equal to 14, right? Okay, so that's another relationship that you can have there that's kind of nice. So there's all kinds of manipulations you can do with these equations. So therefore, if you know one, you can calculate the other, which again is kind of nice sometimes. So the example they have in the book for this one, it says calculate the base dissociation constant for the fluoride ion and the acid dissociation constant for the ammonium ion. Now the reason they're asking for this is because they've given you the, well wait, it's right there. Whoops. Okay, but let me just point this out. In the book, this is the value they actually give you, okay? So what they want you to do is to work out what's the Kb, all right? And it's easy once you know the Ka. The hard part, I guess, is figuring out what is the conjugate acid of this base, right? So you've got F minus, the conjugate acid of that would be HF. So you have to look up the Ka for HF, which we just saw was 1. Did we see that? We sure didn't. 6.8, sorry, times 10 to the negative 4th. Okay, so there's your Ka value, so then you just plug that into the equation. Ka times Kb is equal to 1.0 times 10 to the negative 14th. Solve for Kb, and that's going to give you that, oops, I went the wrong way. That's going to give you that 5 or 1.5 times 10 to the negative 11th number. Okay. Same thing with the NH3. Well, okay. See, I said NH3, but again, that's making an assumption here. NH4 plus is the ammonium ion. If we want to know the acid dissociation constant for that, what we've been given in the book before is the base, the Kb for NH3, right? Which is the conjugate base of that. So you're going to see this on the AP exam sometimes. They will ask you a question about an acid, but all they've given you is a base reaction and the Kb. And you have to realize, oh, we're dealing with the conjugate acid of that base. All right, so I'm going to give you some example problems from old AP tests that kind of show that. And basically this equation will help you sometimes when you get stuck. It's like, oh, I don't know the Ka for this problem. I can't solve it without the Ka, but maybe earlier in the problem they gave you the Kb. And as long as you recognize, okay, that's the conjugate acid, then you can use the equation Ka times Kb equals Kw to figure it out. It's maybe worthwhile to say, maybe it's obvious, this only works, the Ka times Kb equation only works when you're dealing with conjugate acids and bases, right? So I can't say, oh, I know the Ka for HF, so I'm going to find the Kb for NH3 using this equation. I mean, obviously that doesn't work, okay? You have to use HF and F minus, okay? And that's when this equation works. So that's pretty much it. So, I mean, we've covered the kind of the big stuff, and then everything else that we need to cover in this chapter will just be a little bit of an extension of that. But as far as the big, heavy mathematical stuff, I think we're pretty much through it. So then, I don't know how to end right now, but we're done. We're basically done. So you guys can stop watching this video now because it's over. All right, see you Monday. Most awkward.